Welcome to this video tutorial. My name is Mark Scythian. The date today is January 12th, 2023. In this particular video tutorial, we will be covering DC series parallel complex electrical circuit analysis. So here we have three sensors on an airline transport avionics application powered by 440 volts AC, then rectified to 440 volts DC. So the assignment specifies to compute the DC voltage, current, and power at sensors A, B, and C. So we can start by establishing the series resistors R1, R3, and R5, and their responsibility is to drop voltage on series pathways, and series electrical pathways maintain constant current. Next, we have the parallel resistors R2, R4, R6, and their responsibility is to induce current draws, maintaining constant voltage on parallel electrical pathways. So next, if you're using your calculator to combine resistors in parallel, the subcomponent specified can also be the quantity of 1 divided into R to the -1 power on your calculator. So we start by combining resistors 6 and 5, and note that they make a series connection. So when combining resistors in series, the combination is additive, so we just simply add these two. And then we continue on and combine R6, R5 with R4, and the combination is in parallel with R4, so we can use the inverse sum rule, and you would enter it in two open parentheses, 1 divided into 40.25 close parentheses plus open parentheses 1 divided into 75 close parentheses, and a second close parentheses, and then exponential -1, and this then yields 26.2 ohms. And then we carry on and combine resistors 6, 5, 4 with 3, and they make a series connection with R3, so we just add 1.0 ohms, and we compute 27.2 ohms, and then we continue on and combine resistors 6, 5, 4, 3 with 2 in combination, and they make a parallel relationship. So we can then combine this with resistor 2, and we compute 17.6 ohms, and then finally we combine resistors 6, 5, 4, 3, 2 with 1, and of course they make a series relationship, so additive rule, we compute a total resistance for the entire circuit of 18.1 ohms. So we can make an account of the calculation below. So the R sub T, the total resistance for the circuit, is 18.1 ohms. Then we access Ohm's law, which is voltage E is equal to current I times resistance R, and then we can solve for the I, or current component, E divided into R, which then allows us to solve for the total current, and that is equal to 24.3 amps. So we can document that down here below as I sub T. So next we start with the total current as the source current, and in DC electrical flow, electrons flow from positive to negative. So the total current will start at the source, the positive terminal output, starting to flow to resistor 1. So we must compute the voltage drop at resistor 1, so ER1. We can access Ohm's law, 24.3 amps times 12.5 ohms. So we have a voltage drop of 12.15 volts DC. So we can enter that in here. And then we move on and compute the voltage flow or flowing to resistor 2, ER2. So this then becomes the source voltage, which is the total voltage 440 minus the 12.15 volt voltage drop at R1. So 427.85 volts DC will flow to resistor 2, and then we compute the current draw at resistor 2 IR2, which is Ohm's law solving for current. So 427.85 volts DC divided into 50 ohms. The resistance value of R2 is 8.6 amps at R2 is the current draw. And then we must compute next the current flowing to resistor 3, which is IR3. And this is simply the source current 24.3 minus the current draw at parallel resistor 2, R2. So then 15.7 amps flows to R3. Next, we compute the voltage drop at R3, which is ER3, Ohm's law. So 15.7 amps times 1.0 ohms. There will be a 15.7 volts DC voltage drop at R3. Next, we compute the voltage flowing to R4, ER4. So this is 427.85 volts DC at R2 minus the voltage drop at R3, 15.7. So 412.15 volts DC flows to R4. Next, we have the current draw at resistor 4 or IR4. So this is Ohm's law solving for current. So 412.15 volts DC divided into 75 ohms, which is the resistance value of R4. So this is 5.5 amps at R4 is the current draw. And then the current flowing to R5 is IR5. So this is 15.7 amps, which flows to R3 and would continue to flow to R5, but there is a parallel current draw at R4, so we have to subtract that from 15.7. So 5.5 amps subtracted from 15.7 amps is 10.2 amps, which then flows to resistor 5, R5. Then we carry on and calculate the voltage drop at R5, ER5, which is 10.2 amps times 0.25 ohms, Ohm's law. So we compute a voltage drop of 2.6 volts DC at R5. And then next we compute the voltage flowing to R6, ER6, which is 412.15 volts DC as it is on R4, minus the voltage drop at R5 in series. So the voltage flowing to resistor 6 is 409.55 volts DC, so we write that in there. And then we compute the current draw at resistor 6, IR6, which is Ohm's law solving for current. So 409.55 volts DC divided into the resistance value of R6, 40 ohms. And this equates to 10.2 amps is the current draw at resistor 6. So computing the remaining current to ground would be the 10.2 amps flow at R5 minus the 10.2 amps current draw at R6. So 0 amps flows to ground, so this is a balanced circuit. And then the remaining voltage to ground is 409.55 volts DC minus 0 volts, no more voltage drops, so 409.55 flow back to ground. And it should be noted that open circuit, or the system connected but turned off, the switches opened or shut off, we still have voltage load but no current. Whereas when we switch on the circuit, closed circuit on, we have both voltage load potential and current. So the voltage then finds its way back to its source without any incurrence of electron discharge. So next we have to solve for power at the sensors. So let me go back there went a little faster. So power is I current times V voltage. And the units are measured in watts. So we can compute the power draw at sensor A. So this is PR2, 8.6 amps times 427.85 volts DC translates to 3,679.5 watts at sensor A. So we write that in there. And then sensor B, the power, it's PR4 for sensor B. And so we have 5.5 amps times 412.15 volts DC to compute 2,267 watts of power draw at sensor B. And then sensor C, that's designated as PR6, is 10.2 amps times 409.55 volts DC, which computes to 4,177.4 watts. And then we write that in there next to C. So then we do a final specifications accounting, listing the total current, total voltage, and total resistance. And then finally we answer and complete the assignment by specifying the voltage, current, and power metrics for each sensor A, B, and C, respectively.